Hi guys. So we'll continue our course on the AI agents in LangGraph uh, by deep learning, which is given by LangChain and Davidi. Um, LangChain is the framework for building a a flow based um, if flow based steps, not the flow based, what you can actually say. Mm, let's make it quick because there's no time. Um, the Once you call an LLM model, it gives you a response, right? So the response is smart enough that it can actually give you reasoning also. So people have got a thought saying, what the if the thoughts are converted to actions, right? So if if it has additional capability, how can we give additional capability to an LLM model which is already smart? So for this thinking, the thought process is uh, giving it more tools. So uh, but these tools needs to be used, the right tool should be used the right time, kind of stuff, and at the same time it should be incremental to the model, right? So you ask the model, it gives it an output, and then we use certain tool, fetch additional information, or get some specific task done, and then you go back to LLM and say, okay, this is my prompt, this is the action we thought you should do, and this is what I have done. So this is the output, kind of stuff. So then we give that output of that particular action to the prompt again, and then say, okay, this is what has happened. And the LLM is smart enough that it can actually say what is the next logical step, kind of stuff. Say what should be the next action, kind of stuff. Then you perform that action. So it's lang chain is nothing but we are chaining whatever actions that needs to be, that needs to be done. We are chaining them together in steps, and we are also using external tools which are required. For example, initially, but even GPT-4o is able to do, but GPT-3, if you see, the limitation is it can't do a dynamic search and fetch the results from outside and then use them. So even now, 4o is limited search, kind of stuff. It is not a global search, as far as I know. So what they we used to do is in LangChain, you call a model, it gives you answer as per what it knows. It doesn't understand what it doesn't know. So for example, if you want to know what's the weather today in specific place, and basing on that you want to make some travel planning and other stuff. So but the LLM model doesn't know what is the weather today, it's a dynamic number, right? So what we could do is and we'll create an action there to find out the present weather in some place, and then we will use a tool that is like yeah, calling an API or something like that, and then we fetch the weather using that API, and then basing on that we will um, take the next steps. So getting the current weather in a specific place, or the weather forecast of specific day in a specific place. Let's assume that uh, that's one of the inputs that is required for our agent to work. But we LLM hasn't have that capability, so we complement that gaps using these additional tools and stuff. So that's what it is briefly, but let's understand more about it the further lesson kind of stuff. Okay. Let's share and entire screen. This one. To share audio, share a tab instead. Oh, okay. Chrome tabs, agents. Beautiful. So now I'm sharing a specific tab, which is very good. So Oops. Why did I pick up agents? It's DLAI. Okay, let's reshare. Dampen. Share this tested, yes. So mode here. Nice. So we'll play this.
Welcome to AI Agents in LangGraph, built in partnership with LangChain and Tivoli, taught by Harrison Chase, co-founder.
Let's quickly recap on this.
In the last lesson, you built an agent from scratch. Now, let's implement the agent using the LangGraph, and along the way, introduce some of its components and features. All right, let's get coding. All right, so let's break down what exactly we did in the last lesson. We had this user message that came in. We then had the system prompt, and this was this very long one. We then called an LLM with that. This outputted something like what's right there, a thought and an action. Based on that, we then made a decision. We would either return or we would call a tool. And we put this all in a big loop, this query function. And we had these two tools that we would call, calculate and average dog weight. And if we called the tool, we would get back an observation, and then we'd loop back in to the prompt and would put that observation as a new message. So let's break this down into LangChain components. First, let's talk about prompts. So prompt templates allow reusable prompts. And what this basically means is that we can create something like this right here, a little string with some formatted variables that we can replace. And so those formatted variables can come from user content. So we can have this prompt template that we format in different ways depending on the user content. If you want to see a bunch of examples of these prompt templates, you can actually see them in the LangChain Hub. So here's one that's very similar.
Oops, sorry.
In the last lesson, so here's one that's very similar to the agent prompt that we just used. So you can see here, it says, answer the following questions as best you can. You have access to the following tools. And here we don't hard code the tools themselves, but we have this little variable. And same with tool names down here. And then we have the input here, and this is the user question, and then the agent scratchpad. And these are all the actions it takes and the observations. If you want to see more prompts, you can go to the hub here, and you can see a bunch of prompts that people in the community have contributed. The next component in LangChain that we have is tools. So here's a Tivoli tool, and this is the search that we will be using from here on out. You can see that we import it from the LangChain community package, which contains hundreds of other tools. Maybe the biggest part of this application, the most code that we wrote, was this function that would loop. And that's represented by all these arrows here. And that's one way to think about LangGraph. LangGraph helps you describe and orchestrate that control flow. Specifically, it allows you to create cyclic graphs, which is exactly what we have here. It also comes with built-in persistence. And this is really nice for having multiple conversations at the same time or remembering previous iterations and actions. This persistence also enables really cool human-in-the-loop features. If you look at these diagrams here, and these are all diagrams of agents from academic papers, these are all represented as graphs. And that realization was what led us to create LangGraph, an extension of LangChain, specifically aimed at agent and multi-agent flows. Crucially, it allows for really controlled flows. So in these diagrams, there's really specific arrows leading from one box or state to the next. We've seen that this controllability is crucial for creating agents that can perform well. Three of the core concepts of LangGraph are nodes, edges, and conditional edges. Nodes are agents or functions. Edges connect these nodes, and then conditional edges are used when you need to make decisions about which node you should go to next. So let's take a look at an example of a LangGraph you can create that is equivalent to the function that we wrote in the lesson before. We can have an agent node. This is the LLM. We can then have a conditional edge, which takes the result of that LLM call and decides what to do next. One of those edges can be an action edge, which calls a function node, and that automatically loops back to the agent node. There's an entry point, which is where you start, and then there's the end node, which is the other action available to take after the agent. One of the most important things to understand when working with LangGraph is the state that is tracked over time. This is often called the agent state. This is accessible at all parts of the graph, at each node in each edge. It is local to the graph, and it can be stored in a persistence layer, meaning you can resume with that state at any point in time later on. Looking at 2 examples, we first have a simple state where we just have this list of messages. Taking a closer look, we can see that this message variable is a sequence of base message. Base message is a LangChain type. It's annotated with operator.add. This means that when the state is updated with new messages, it doesn't override the existing messages, but rather it adds them to that state. Let's take a look at a more complex state. Here we have input, chat history, agent outcome, and intermediate steps. They all have their own different type. 3 of them are not annotated in any way. This means that when a new update is pushed to that variable, it overrides the existing value there. However, intermediate steps is annotated. It's annotated with operator.add, which means that when a new update is pushed there, it adds to it. This makes sense because intermediate steps is what is tracked as the agent action and agent observation throughout the graph as it executes. And so we want to continuously add to that as more and more actions are taken. Getting really specific about the previous agent that we created and how that would map to a LangGraph object, we can see that we will have one node. We'll call this call OpenAI, and this will call the LLM. We'll then have a conditional edge, which will check for the existence of an action to take. And so we'll call this exists action. And then we'll have another node which actually executes that action. We'll call that take action. And the state that we'll track is pretty simple. It's just this list of messages to which we add over time. With that high-level overview, let's dive into the code. Let's first load in any environment variables that we're going to need to use. This is our OpenAI API key. We're now going to import a bunch of things that we need to create these tools, agent state, and the LangGraph itself. First, let's import state graph and this end node from LangGraph. We'll see how we'll use those later on. These typing imports and operator are used to construct the agent state. We then have all these different message types. These are LangChain message types that we'll use to represent the human and AI and system messages. From LangChain OpenAI, we're going to import chat OpenAI. This is a LangChain wrapper around the OpenAI API. This exposes a standard interface for all language models, meaning that even though we're going to use chat OpenAI for this lesson, we can actually switch it out for any of the language model providers that LangChain supports without having to change any other lines of code. Finally, we're going to import Tavily, the search engine that we're going to start using as the tool in this example. Let's first take a look at the tool. We'll create the tool by initializing Tavily search results with max results equals 2. This means that we'll only get back 2 responses from the search API. We can see that it's of this type, and it's got a specific name, Tavily _search_results_JSON. This is the name that the language model will use to call this tool. Let's now create the agent state. This is exactly what was in the presentation. It's just an annotated list of messages that we will add to over time. Let's now create our agent. As discussed, we're going to need 3 functions. We're going to need 1 function to call OpenAI, 1 function to check whether there's an action present, and another function to take that action. These will all be different methods on this agent class. So let's create those first, and we can then see how they interact with each other. Let's now create the agent class. we're going to want this agent to be parameterized by 3 different things: a model to use, the tools to call, and the system message. As before, let's save the system message as an attribute. We're now going to start creating the graph. First, let's initialize state graph with the agent state. Right now, this graph is pretty bare. It doesn't have any nodes or edges attached to it. We know that we're going to want to create those 3 functions before and use them, 2 as nodes and 1 as edges. So let's sketch it out, and then we'll implement those functions as methods on the class. So first, we know that we're going to want to create a node called LLM, which will execute the LLM. And we can do that by doing graph, add node, LLM, and then we're going to need to come back here and we're going to need to pass in the function that we want to represent this node. We'll add another node, the action node. We'll do the same thing here. Now we're going to add that conditional edge. This goes after the LLM is called. It checks whether there's an action present. If there is, then it goes to the action node. If there isn't, then it goes to the end node and it finishes. So let's add this. Again, we'll have to add the specific functions later on. The first argument we pass in is the node where the edge starts. This is from LLM. The second argument we pass in is the function that'll determine where to go after that. We're going to implement this later on, so we'll leave this blank. The third and final argument that we're going to pass in is a dictionary representing how to map the response of the function to the next node to go to. So if the function returns true, then we're going to go to the action node. If it returns false, then we're going to go to the end node. We're now going to add a regular edge. This is going to go from the action node to the LLM node. So we can do this calling add edge. The first argument is the start of the edge. The second argument is the end of the edge. We're then going to set an entry point for the graph. This is at the LLM node. With that done, we can compile the graph. Graph.compile is just what we need to call after we've done all this setups, and we'll turn it into a LangChain runnable. A LangChain runnable exposes a standard interface for calling and invoking this graph. We'll see more about that later on. We'll save this as an attribute on the class. We'll also save the tools and the model that we passed in. For the tools, we'll create a dictionary, mapping the name of the tool to the tool itself. For the model, we'll actually call bind tools on the model, passing in the list of tools that we passed into the agent. What this is doing is this is letting the model know that it has these tools available to call. All right, so we've created this graph, but we still need to create 3 things. We need to create the function representing the LLM node. We need to create another function representing the action node. And we need to create a third function representing this conditional edge. We'll add all of these as methods on this agent class. For the LLM node, we're just going to create a function called call OpenAI. It's going to take in this state, this agent state. All of the nodes and the edges will take this in. What we'll do is we'll get the list of messages from this state. We'll then add in this system message, and we'll then call the model. We'll then return this dictionary with a list of messages, but there's only one message in it. It's the message that's returned from the model. Again, remember, because we had annotated the messages attribute on the agent state with the operator.add, this isn't overwriting this. It's adding to that state. We can then go back to the graph.add node and change that to pass in this method. Let's now do the same for the action node. The action node will also take in this agent state. We'll get the last message from the list of messages. We know that if we've gotten to this state, the language model must have wanted to call some tools. That means that there will be this tool calls attribute present on the last message in the agent state. Crucially, this can actually be a list of tool calls. So a lot of the more modern models support parallel tool or parallel function calling. What we can now do is we can loop over these tool calls. We can find the relevant tool by looking up tool name in the dictionary of tools that we created. We can then call invoke on it, passing in the arguments that we have from this tool call. We can then append this as a tool message to this results list. And then we're returning this messages mapping to this results thing. Again, this is just the new messages that we need to add. What's happening under the hood is that LangGraph is adding that to the state in between iterations. We can go into the method. We can see first it calls Tavily with the query a little bit different from parallel function calling. It's not happening in parallel, it's happening sequentially. And the reason it's happening sequentially is it actually needs the result of the first query in order to make the second query at all. With this, we've seen how we can take that raw LLM and raw Python example with some fake tools and turn it into a real agent that can answer complex questions. Under the hood, it's using the Tavily Search API. In the next lesson, we'll learn a lot more about that.
A frequently used tool in agent is search. This lesson is going to dive into how agentic search is different from standard search and how to use it. Let's try it out. All right, so before diving into what an agentic search does, let's understand how an agent might use it. In a zero-shot learning, an agent would receive a prompt and will produce an answer based on its static weights of the model. As powerful as it's proven to be, there are many limitations to this process. First, the data around us is dynamic, so we couldn't, for instance, ask about the scores from the game last night. Secondly, in many use cases, we would want to know the sources of the information provided in the result. This can reduce hallucinations and smooth the friction of this human-computer interaction. Looking at the slide, we can see the prompt is received by the agent, which then decides to call the search tool. Then the information found is returned to the agent. Now, let me show you what happens inside. This is an example of a very basic search tool implementation. Let's go over it step by step. If the agent decides, it will send a query to the search tool. The first step would work on understanding the question and divide it to sub-questions if needed. This is an important step because it can handle complex queries. Then, for each sub-query, the search tool will have to find the best source, choosing from multiple integrations. For example, if an agent would ask, how is the weather in San Francisco? The search tool should use a weather API for best results. The job doesn't end with finding the correct source. The search tool would then have to extract only the relevant information to the subquery. A basic implementation of this can be achieved through a process of chunking the source and run a quick vector search to retrieve the top K chunks. After retrieving the data from each source, the search tool would then score the results and filter out the less relevant information. Okay, so let's test it out. Okay, so first let's import some libraries and do the initial connection to the search tool. Here, we loaded Tavily API key from the environment variable. And then we create the Tavily client, which we imported from the Tavily library. All right, so after creating the initial connection, let's test it out. Here I'm gonna run a search, asking about NVIDIA's new Blackwell GPU. And let's see what's the answer. All right, so as you can see, there's a pretty simple answer, but very accurate. Okay, so let's do a simple example to see the difference between a regular search tool and an agentic search tool. I'm gonna create a simple query about the weather in a certain location. Feel free to change the location to your location. I'm gonna do it with San Francisco. So the query is, what is the current weather in San Francisco? Should I travel there today? Now let's try to attempt it with regular search. Here, I'm gonna import the DuckDuckGo search. I'll try to run a regular search and get the links that might lead me to the answer. Okay, so as you can see, we did get the results. but it's not what the agent needs. Now we're gonna have to get some answers from these results. Let's do that. Okay, so now we're gonna create a function that's gonna scrape the data from the first URL. We're gonna use Beautiful Soup to extract the HTML. As you can see, that's a beautiful output. And if you want, you can keep scrolling down. But let's try to clear it up. Okay, to clear it out, I'm gonna use some parsing. I'm gonna extract the headers and some content. I'm gonna strip it down and use join to get the text. As you can see, the output is much, much better, but still not concise enough. Okay, after seeing this, let's try to run it using the agentic search tool. We're gonna do the same query and call Tavili to get us the results. As you can see, we got a simple JSON with a lot of information about the weather in San Francisco. Let's clear it out so we can see a formatted JSON. Okay, now we'll parse and highlight the JSON just so we can see it clearly. As you can see, this is not the answer I would want to see as a human, but this is the exact answer an agent would want, a structured data. Okay, I'm going to load the sample from Google search so you can see the difference. Here, I get exactly what I want as a human. A nice image showing me the temperature, the humidity, the wind, but not unnecessary data. That's exactly the difference between what a human needs and what an agent needs. Okay, that was an introduction to agentic search. In the next lesson, Harrison will discuss persistence and streaming.
So this Travelly's code is this all is explaining how it is done without using Travelly. Use Travelly, it is gonna be very fast. Here you should search with the city query. No, query is already there, so I can use the query. Why didn't he do that? No. The current weather underscore access is temperature of 23.2 degrees centigrade. It's coming from us, coming from east. 78% is the forecast for it before traveling. Okay, that's also has going to rain today. Let's go. This is a little complex. Let's see how it works. Did you do all of that? I doubt it. That's interesting, no? So it is broken down all the 3 places. I need to have sent it there. Let's see some place where it's raining. Let's try Hamilton. Yeah. According to there's no mention of the focus for today. However, it is recommended to check for budget to the time you are interested. For Hamilton, Texas, the provided source. Oh, come on, man. Okay, let's go to Florida. Okay, go back. Go back. Rain locations. Here it is raining heavily now. This place is. Heavy rain falling. Punta Gorda. Florida. TNT. Sorry, yeah, let's say. So there is 30% chances of showers and some San Francisco, Texas today. Oh, if I say Frisco, Texas, it's being more clear. Evident and no specific information. Sorry. No, Texas. Let's see. Frisco, Texas today. No, how can it be, man? There's something wrong with it. No, it's not fair. Texas. Clouded. This is complex search. Here is our distance of 40 minutes and traveling from Dallas, Texas to Kingston, Texas. Please get Kingston. Point Texas. It doesn't give the places in between. Okay, that's okay, fine. Maybe auto short monitor of the system is enough. It got one place, but maybe it would get. This is nice. It's working, man.
When building agents, they're often working on longer running tasks. For these types of tasks, there are two really important concepts: persistence and streaming. Persistence lets you keep around the state of an agent at a particular point in time. This can let you go back to that state and resume in that state in future interactions. This is really important for long-running applications. Likewise, with streaming, you can emit a list of signals of what's going on at that exact moment. So for long-running applications, you know exactly what the agent is doing. Let's see these concepts in action. So to get started, let's create our agent as we did before. We'll load in the appropriate environment variables. We'll make the necessary imports. We'll create our Tavily search tool again. We'll create our agent state. And finally, we'll create our agent again. Now we're going to add in persistence. In order to deal with persistence, we've added the concept of a checkpointer into LangGraph. A checkpointer basically checkpoints the state after and between every node. To add in persistence for this agent, what we'll do is we'll use a SQLite saver. So this is a really simple checkpointer that we've added that uses SQLite, a built-in database under the hood. And we'll just use the in-memory database. So if we refresh this notebook, it'll disappear. But you can easily connect this to an external database, or we also have other checkpointers that use Redis and Postgres and other more persistent databases like that. Once we initialize this checkpointer, the way that we can use it is we're going to pass it in to graph.compile. So in order to make this easy, let's add another parameter to agent that is checkpointer. And then we're just going to pass checkpointer equals checkpointer right here. And we've modified our agent. This is all we're going to need to do. We can now create our agent, and we're going to pass in checkpointer equals memory. And remember, memory is the object that we initialized above. When we use our agent now, we're also going to add the concept of streaming. And there's two things that we might care about streaming. First, we might care about streaming the individual messages. So this would be the AI message that determines what action to take, and then the observation message that represents the result of taking that action. The second thing we might care about streaming is tokens. So for each token of the LLM call, we might want to stream the output. To begin, we're just going to start by streaming only the messages. We'll do the tokens later on in the lesson. So we're going to create our human message. What is the weather in SF? This is the one we ran before. We're now going to add this concept of a thread config. So this will be used to keep track of different threads. When building agents, so this is a really simple checkpointer that we've added that uses SQLite, a built-in database under the hood. And we'll just use the in-memory database. So if we refresh this notebook, it'll disappear. But you can easily connect this to our human message. What is the weather in SF? This is the one we ran before. We're now going to add this concept of a thread config. So this will be used to keep track of different threads inside the persistent checkpointer. This will allow us to have multiple conversations going on at the same time. This is really needed for production applications where you generally have many users. This thread config is simply a dictionary with a configurable key. And as part of that, we have a thread ID, and we can set that equal to any string. Here, we're going to set that equal to 1. We're now going to call the graph not with invoke, but with stream. We're going to pass in the same messages dictionary, and we're also going to pass in this thread config as a second parameter there. We're then going to get back a stream of events. These events represent updates to that state over time. Because we know our state only has one key, the messages key, we're just going to loop through it and print that out. So let's run this and see what happens. We can see that we get back a stream of results. First, we get back an AI message. This is the first result from the language model, and it's telling us to call Tavily. Next, we get back a tool message. This is the result of calling Tavily, and it has the results from the search. And finally, we get back a third AI message. This is the final result from the LLM answering our question. With this stream method, we get back all of these intermediate results, and we have really good visibility into what exactly is going on. Let's now call it with another message. This time we're going to say, what about in LA? So this is continuing the same conversation that we had before. It's asking a follow-up question. We don't say anything explicitly about the weather, but based on it being a conversation, we would expect it to realize that we're asking about the weather here. In order to make sure that we're continuing from that same point, we're passing in the same thread ID here. If we run this, we can see that it returns first a function call where it's looking for current weather in Los Angeles. Again, it's knowing that we asked about weather because it has this persistence from the check pointer. We can then see that it's getting back results from Tavily. And finally, that it's responding with an AI message that says the current weather in Los Angeles is blah, blah, blah. We can call this yet again using the same thread ID with the message, which is warmer. Here it has access to the full history, so it can accurately respond, Los Angeles is currently warmer than San Francisco. Just to demonstrate the importance of this thread ID, let's change this to be 2. If we run this now, we can see that the language model is really confused. Can you please specify the 2 or more items you are comparing to determine which is warmer? That's because it doesn't have access to any history. And that's because we're using a separate thread ID. So we've covered the importance of persistence, and we've showed how you can stream events. But what about streaming tokens themselves? For that, we're going to want to use the aStreamEvents method that comes from all LangChain and LangGraph objects. aStreamEvents is an asynchronous method, which means that we're going to need to use an async check pointer. In order to do this, we can import async SQLite saver and pass that to the agent. This is very similar to before. It's just swapping out a synchronous SQLite saver with an async SQLite saver. This allows us to use async methods on the graph. We'll use a new thread ID, so this will start the conversation from fresh. We're also going to be iterating over a different type of event. These events represent updates from the underlying stream. What we want to do is we want to look for events that correspond to new tokens. These kind of events are called on-chat-model-stream. When we see these events happening, we want to get the content and print it out. And we'll print it out with this pipe delimiter. When we run this, we should see it streaming real time into the screen. So we can see a few things here. First, we can see that it called the function under the hood. The reason it didn't stream out anything there is there actually was no content to stream. It was just a function call. But then we can see that when it did get to the final response and it is returning a final answer, we stream out those tokens one at a time. We can see that we've got this little funny pipe delimiter here, but we could easily remove that in our production application if we wanted to. So that's it for persistence and streaming. Pretty simple to get started with, but really powerful for building production applications. You're going to want your agents to be able to have multiple conversations at the same time and have a concept of memory so they can resume those conversations. And you're also going to want them to be able to stream both the final tokens but also all of the messages that came before. Persistence is also really important for enabling human-in-the-loop type interactions. And that's exactly what we're going to cover in the next lesson.
Five, 6, 7, 8. Only 3. Friday tomorrow. Yeah. Okay, let's stop. Yeah. Let's stop sharing here. Do offline research on Travelly kind of stuff. So the key thing I want to say about this whole agent thing is also in this aspect, especially the persistence and streaming thing that we have seen now. A prompt where a prompt can also be given incrementally, where in the incremental goes, for example, you start with certain question or something like that, and basing on that, you keep adding more messages to it, like a chat, right? Agents are actually more like a chat only, but whereas the answers between the chat, instead of human answering the certain inputs or providing certain inputs or something like that, there are tools or like Travelly is one search-based tool that we have explored today, which will help in fetching some results from online kind of stuff, right? It is coming with an API key. I'm not. I think that is a paid tool kind of stuff. We should look up and see how it works and stuff. Travelly, but you get the results, right? So this is conversation happening. What happens when you're chatting with an agent is the chat actually gets persisted somewhere, either you locally on your system or in the server side. It gets persisted, and that's how they remember what is the chat that's happening. Similar scenario here when you have this agent working on the specific prompt that you have initially given. Then, for example, you can also design it in a way that it should go in a loop, and then it should consistently pull the data from online and then record something. For example, for next 1 hour, consistently, it should actually look through the weather in 15 places, and it actually should give you what is the weather pattern, or we should rate all the 15 places in a way which is having a better weather. Again, better weather is a subjective thing, but let's say where there is less rain, or a comparison between the 15 can be pulled out. So that's a continuous exercise that needs to happen, right? So this can be achieved using a normal program, right? We can do using normal program. But what agents are capable to do is we can achieve all that what I said without writing any program. So agent, by just prompting it, it understands that it needs to search for weather, it needs to search for a certain frequency, and then it understands that you need to do a comparison in between them based on certain factors, and then it understands that you need to order it in particular ranking or something like that. So this all could be done just by giving a text, specific text with certain values and stuff. So that's the beauty of LangChain and agents and all that stuff. So I'm pretty sure there will be a library of agents that are available, which will be running on individual systems. And as he has shown that we can also make them parallel, like the tools that are there, those can work in parallel. Even the models can work in parallel. So what happens, how it speeds up is you use 4 agents or 5 agents, and each agent will work in parallel to fetch information. For example, one will fetch the road conditions, one will fetch the weather conditions, one will see if there is any see if there is any kind of activity that is going on. Like it will fetch all the information that is necessary, and then it can give us a summary saying, okay, this is what is the plan. Like travel planning and all that could be automated and could be very nice with these agents. So we'll see more about the agents in the rest of the course. Okay. Thanks, guys. Have a good day.